Good afternoon. This is our Aerodynamics 1 course. It is about incompressible flow. So we'll discuss what an incompressible flow means because we have different types of flow from that. I think you are familiar with what is an incompressible flow, what is compressible flow. So we'll discuss on it, but the course is about incompressible flow or the fundamental aerodynamic course, because there is a continuation of another aerodynamic that part 2 that is about compressible flow. The first chapter, the objective of actually this course is to understand the basic property of fluid flow, to know the different conservation principles like mass, momentum, and energy conservation laws, to calculate flow fields, velocity, streamline, vortexes, and circulation, to solve airfoil problems, and to understand the potential flow in 2D and 3D airfoils. And finally, to calculate the lift and the drag of one-dimensional wing as well as finite wing, what it's called, 3D wing. So we'll cover these topics in the first chapter. So let me go directly to the parts. So I think it is better to start from the basic definition of aerodynamics. We already actually defined aerodynamics in our flight principle course. And most of the part of aerodynamics is already touched with that course. However, it is better to review the fundamental definition of aerodynamics and what are the aerodynamics quantities which we are going to optimize through the knowledge of aerodynamic course. So the definition of aerodynamics itself is it is the study of motion of air and the force acting on the bodies which are moving through the air. So it is simply the study of the behavior of air as the air interacts with solid objects, such as an aircraft, such as cars, such as missiles, and other objects which are flowing through the air. So aerodynamics is just a branch of science and engineering that deals with the study of how the gas, particularly our gas here is, in the context of aerodynamics, it is air. So how the air interacts with the moving object. So our moving object is an aircraft. It can be a missile, it can be a balloon, or any kind of object which flows through the air. So the fundamental focus of this course is to understand and to calculate what is the lift force, what is the drag force, what is the moments which encounter in the object which are flowing through the air, and the motion resulting from the air which interact with the object. So that is our fundamental concept. So in the study of aerodynamics, this aerodynamics plays some crucial role in the design and performance analysis of aircraft. Okay, so the aircraft performance, when I say aircraft performance, the lift performance, the climb performance, cruise performance, descent performance. It can be also the performance related with landing and the takeoff performance. So all these are crucial points of the design of aircraft. So we already discussed the mission profile of aircraft in our fundamental course of the principle of flight, so that all those mission profiles must be optimized. So in order to optimize that, we have to know the aerodynamics, because the aerodynamics quantity, the aerodynamic quantities are the major quantities which plays crucial role in the design. So when an aircraft moves through air, it experiences the effect of fluid's motion. That because it creates a shear. That means because of the presence of viscosity in the air, it creates shear force, and there is also a pressure distribution. So the shear force and pressure distribution are the forces which enable us to the aircraft to be airborne. So this interaction between the aircraft and the air generates force. So these two fundamental forces are the shear force and the pressure. Okay, that affects the aircraft's motion. So as you see here, this is the CFD simulation of aircraft. As aircraft is flowing through the air, in your computational fluid dynamics course, you can simulate this thing. How the aircraft interacts with the air, and the air interacts with the aircraft also. So that are the some kind of CFD simulation to visualize the interaction between aircraft and the aerofoil. Okay, so aerodynamics are generally concerned with one or more of the following. One is the prediction of force, moments, and heat transfer. So from your thermodynamic course, how heat can transfer from one system to another is the part. So it includes the part of thermodynamics also. The prediction of forces like lift force and drag force, the prediction of moment. There are three different moments, like pitching moment is there, yaw moment is there, roll moment is there. So in order to balance an aircraft in a stable condition, we have to know these forces and these moments, okay? So once we know them, then we'll design an appropriate aircraft. The second is actually that part is called external flow or aerodynamics. And the second one is internal flow aerodynamics, which is related to determination of flow, fluid flow characteristics within ducts. This within duct is related with like the flow through the engine, aircraft engine, through the engine. Hot combustion gas are flowing through the combustion chamber, and then it goes to the turbine, and through the exhaust it comes out. So the imparting of that hot liquid, high pressure hot liquid or fluid, the momentum effect will help us to push the aircraft forward. So the dynamics of actually both liquids and the gas are studied under a general course, as you have discussed in your fluid dynamics. It is just fluid dynamics course. It may contain hydrodynamics, gas dynamics, and aerodynamics also under this. So the basic concept of all fluid dynamic parts are fundamental for us now. So you have to go through your fluid dynamic course in order to understand this course. So what are the fundamental principles which are to be obeyed in the study of aerodynamics? Those three continuity principle, Bernoulli's principle, and the Newton's third law principles are the main principles in addition to the thermodynamic principle. In addition to this, you have thermodynamic principle. Actually, thermodynamics principle also consists these things in it. Yeah, so what the continuity principle means, that is just a conservation of mass. The mass flow rate, which is equals to density times area times, that is flow velocity. Density, area, and flow velocity. The product of density, area, and flow velocity is considered constant at every point from the point of continuity principle. So m dot means that is dm over dt, the rate of change of mass per time. For example, when I say mdt, that m dot is the flow of fuel from the combustion chamber. So the fuel is continuously burning in the combustion chamber and coming through the exhaust. The hot gas comes through the exhaust. So in the exhaust, there is convergent divergent nozzle on which there is a narrow section, which is what we call throat. So area 1, area 2, area 3, you can take different sections and then you can make analysis. So the mass flow rate or M dot is what we call the continuity principle. Okay, so this principle implies that when air flows through the constricted area, for example, you can see here a constricted area having variable sections in the area. Okay, so velocity at point 1, velocity at point 2, velocity at point 3. So we can say rho 1, A1, V1 is equal to rho 2, V2, A2, V2. And then you can equate it with, so that is constant. That the meaning is what we call the continuity principle or conservation of mass. The second one is Bernoulli's principle. That is what we call the conservation of energy. So as you know, the energy principle, energy is neither created nor destroyed, but it can conserved. So according to the Bernoulli's principle, the relation between pressure, velocity, and elevation. Elevation means, let me go to this, the Venturi apparatus or the Bernoulli's apparatus. On that, there may be some reference point here, reference location. Jaime, sorry, I'll come back. Hello? Sige. So pressure energy is there. Again, we have kinetic energy. Again, rho GH is potential energy. The sum of pressure energy, kinetic energy, and potential energy is constant according to Bernoulli's principle. So this pressure energy, rho V1, P1 half rho V1 rho GH1, which is equal to P2 plus half rho V2 square plus rho GH2. So actually H1 and H2 are constant here because we have no altitude difference. At every point, the equipment will have same altitude so that we can remove the H1 and H2 are the same. Gravity is also the same, density is same at the same level, so that we can cancel it. We have left what? The pressure energy and the kinetic energy part. So it is just kinetic energy per unit volume. And we call it as the dynamic pressure. Half rho V square is called dynamic pressure. So static pressure plus dynamic pressure is equals to constant. That is the meaning. So P plus half rho V square plus rho GH is equal to constant, what we call the Bernoulli's principle. So this means what? As the speed of the airflow increase, it is static pressure decrease. And the principle fundamental to the lift generation over aerofoil, that is the meaning. We already discussed how the lift will generate over the aerofoil in our previous course. So in the aerofoil, at the top section, there is a cambered aerofoil effect. And because of that, there is high velocity. The point where high velocity is there, the pressure is low. And at the bottom, there is low velocity. And the point where low velocity there is high pressure. So they compensate to each other. By that, due to the presence of the pressure difference between the lower and upper surface, what you can get? The lift. So the lift generation is related to the Bernoulli's principle. So that is what we have discussed in our previous course. And the third one is the Newton's second law, which is what we call momentum conservation. So momentum means, yeah, MV. the momentum, which is equals to m times velocity, which is constant. So momentum is conserved means it is related to Newton's second law. So we can define Newton's second law, dmv over dt. That is the rate of change of momentum. Okay. So you are familiar with first law, you are familiar with third law. So the third law also is related with the action and reaction, the thrust production of an aerofoil. Also, the third law also is helpful for determining also lift also. So these are the three Newton laws. Particularly, third law is the momentum law. So this is your momentum law, okay? Newton's third law effect, action and reaction effect. As the engine pushes forward the rocket and the rocket exhaust flow pushes backward. So the action and reaction between the two produces the forward motion of rocket. So that is the third law of motion. And the lift generation is related with the as the wing pushes down, air again pushes back. That is action and reaction. So it also the Newton's third law contributes to the lift generation also. Okay, so another important term here is the viscosity and boundary layer theory. So whenever we are learning about fluid related subjects, we have to know the boundary layer theories and we have to identify what is viscosity and what is its effect. So viscosity is just a fundamental property of fluid that describes its internal resistance to the flow or its deformation. So viscosity measures how easily one layer fluid slow over another, or when a fluid flow subject adjacent layer move at different. Actually, you know this stationary plate and movable plate experiment. I'm quite sure you have done it in your fluid course. So one of the plate is considered movable and another one is fixed. Through in between them, we will put viscous fluid. So then the movable fluid creates a shearing effect over that. So that creates a shear force. So that shear force is mathematically related by dynamic viscosity and the velocity gradient. So dynamic velocity times velocity gradient gives you the shear force. So tau of the fluid, which is equals to mu times dv over dy. So that is from the experiment of movable and fixed plate experiment in your fluid dynamics course. So here, tau is the shear force, which is given in Newton per meter square or in Pascal. And mu is dynamic pressure, unknown dynamic viscosity, which is given in Pascal second. And the dv over dy is velocity gradient, which is perpendicular to the direction to the flow. So viscosity arises from molecular interaction within the fluid. So for the gas, viscosity increases with temperature, while for the liquid, it decreases with temperature. That is the principle. Or so near the surface of the body, for example, if you see this aerofoil, adjacent to the surface of the body, what you can see is laminar boundary layer, turbulent boundary layer. There is flow separation point. Some wake turbulence region are subdivided. So that point are called the boundary layer. It is very thin region in which the fluid flow are interact to each other. The aerofoil with the fluid. Okay, and on that you can find one of the point which is known as zero velocity point called stagnation point. A stagnation point, okay, transition point. Again, separation point. That separation point is the point where the lift generation becomes very weak, because the flow behind of separation point is subsonic, and the flow in front of separation point is supersonic, so that the aerofoil will have flow separation occur on that. Okay, once I say this, it is better to review our four fundamental forces of flight. One is the lift force. That is the force that acts perpendicular to the direction of airflow. The drag force, the force that acts parallel and opposite to the direction of flow, which is caused by friction and the pressure difference. And resistance, it is just a resistance force to the forward motion. Thrust is the force that propels, the force which enables the flying object forward, to move forward. That is thrust force. And the weight is the net resultant force which acts vertically downward due to the presence of gravitational attraction. So this weight is as a result of the engine weight, the fuselage weight, the tail section weight, the front section of the aircraft, the landing gear weight. Collectively, we call it as structural weight plus fuel weight plus the payload. So this is called the total weight of an aircraft or the flying vehicle. So weight is the net effect. So this is the four forces: forward force, retarding force, lifting or airborne force, and the force which is moving the aircraft down to the earth. So these four forces are always there in the aircraft. So here also you can observe them. Maybe the thrust force may not be aligned with the velocity vector. So what you can see here is they have some difference. Velocity vector direction and the thrust vector direction are different. In most analysis, we simply align or coincide them in order to simplify our calculation. But in actual case, there is a small angle. Weight is downward. Lift may not coincide directly vertical. Okay. Lift and drag are perpendicular, okay, but they may not vertical and horizontal force. Another important terms are the net resultant force, lift force in vertical upward, drag is in the horizontal, so that we have net resultant force. So this net resultant force acts through the pressure center of pressure. What we call that weight, the weight acts through the center of gravity, because it is the total summation of all forces which acts through the CG. That is called weight. But the resultant force, or the net resultant force of the lift and the drag, or the axial and the longitudinal forces that aligns at the center of pressure. So we have also another word, aerodynamic center also will come later. But now, just remember that your lift will be act through the center of gravity. And we already discussed this. So we have the chord line. The chord line creates an angle with the relative wind direction that is known as angle of attack. So this is the angle of attack. So these are aerofoil terms, actually. Yeah. So the two main aerodynamic forces involved in the here are the drag force and the lift. Actually, others are also the forces, but thrust is the propulsive force. It is due to the presence of power generating systems or the engine, so that we can directly not consider it as aerodynamic force. weight is inertial load. So that we cannot say it as aerodynamic force, but in general, we call them, four of them, as the forces of flight, the four forces of flight. But from them, the two aerodynamic forces are drag and lift. So we will see them in detail. So lift and drag present in integrated effect of continuous distribution of pressure and viscous forces. So due to the pressure and viscous forces, we have drag and lift. So drag is a component of the shear forces. Okay. እስቲ እየሰማችሁ ነው? እየሰማችሁ ከሆነ እስቲ እጃችሁን አንሱ። እየሰማችሁ? ኦኬ። እሺ፣ እሺ። አንስቴብል ኢንተርኔት አንስቴብል እያለ ስለሆነ okay, so lift and drag are always defined with respect to the velocity of the flight. So drag is in the direction of parallel to the direction of flight or stream velocity. Lift is perpendicular to that. So that is the meaning. So we have a direction of flight here, and this is direction of stream. And the inclination is related with the thrust velocity vector direction. Okay, lift is here, drag is here. Okay, and this is the total aerodynamic force or resultant aerodynamic force. You are familiar with that. Lift is equal to half rho v square SCL. So half rho v square is called the dynamic pressure. And S is the rho is the density that depends on the altitude on which an aircraft is flying. V is the flight velocity, or it is equivalent with the stream velocity. S is the planform area of an aircraft, and CL is the lift coefficient. So that is just the meaning of lift. So we already discussed it before. So lift is the force that acts perpendicular to the direction of gravity in opposite direction, allowing the object to rise and remain airborne. So our flight object is becoming airborne because of the presence of lift. So anything that flies must generate lift. Anything that suspend in the air or airborne in the air must have lift. So in aircraft, lift must be greater than its weight to achieve and sustain flight. So that's why the maximum lift to drag ratio, we most of the time we calculate lift to drag ratio. And the lift to drag ratio must be maximum. It should be greater than 10. CL over CD max condition. So different aircraft use various mechanisms to generate lift. So actually it is fact, and the shape of an aircraft is curved in nature. Some of them are actually symmetric. Airfoil may not have such different curve. The bottom and the top may same. However, in most cases, the curved shape or the cambered shape of aerofoils are used, and that camber helps us to increase the pressure difference and to increase the lift. The second aerodynamic force is drag. That is the resistance force experienced by an object as it moves through a fluid, and it acts opposite to direction of motion and tends to slow down the moving object because it is a resistance force. So our main intention is to minimize drag. Minimizing drag is the main intention of the aerodynamic designer, because increasing drag is related with high fuel consumption of the air. Increasing drag related with slow movement, and we cannot achieve the range and the endurance which we planned. Range means the total, the distance that we must cover with an aircraft. And the endurance is the time taken to flight. So our aim is to maximize those things. So when we say drag, different classification of drags are there. Fundamentally, drag is classified into parasitic drag and induced drag. Again, the parasitic drag is classified into three classes, like friction drag, interference drag, and wave drag. Again, friction or form drag is classified into some three sections, like skin friction, pressure drag, additional profile drag. And interference drag is due to interference geometry, because when we are attaching fuselage with wing with fuselage, at the point where they're connected, there is kind of intersection, geometrical intersection happen. That intersection causes a drag also. That is called interference drag. Again, wave drag is also among them. Okay, so parasitic drag is the parasite drag is given with CD naught. It is CD naught. In our drag polar equation, you have CD is equals to total drag coefficient. CD is equal to CD naught plus CDI. CDI is KCL square. CDI is equals to KCL square. So that is from this point. Induced drag is CDI. That is lift-induced drag. So CDI is equal to KCL square, and the KCL square, K is related with the aspect ratio of the wing, the Oswald efficiency factor, and it is also dependent on pi. So pi, aspect ratio, and E, 1 over. So K means 1 over pi, aspect ratio, and the Oswald efficiency factor, or wing efficiency factor. Aspect ratio is by itself is the ratio of B square over S. B is the wingspan of aircraft from one tip of wing to another tip. It is called span. So span square over planform area S gives you the aspect ratio of the wing. So we can directly calculate it from the wing geometry. So these are the two types of drags. You can find drag versus airspeed, D versus V infinity curve. So on that curve, you can see two drag. One is induced drag, and another is parasitic drag. As you see, induced drag decreases with speed. As the aircraft speed increases, the induced drag becomes exponentially decreasing. At the same time, as the aircraft speed increases, the parasite drag increases continuously in exponential manner. And the point where parasitic drag and induced drag intersect is called minimum drag requirement point. That minimum drag is minimum thrust point. So our total drag curve is a parabolic curve. Look, this is a parabolic curve. Why? Because CD is equal to CD naught plus KCL square. Okay? CD is equal to CD naught plus KCL square. So this is a parabolic curve, so that it is in terms of velocity, it's parabolic actually, because drag half rho V square SCD. Okay? In terms of drag and in terms of velocity, it's parabolic. So what you can observe is total drag is a parabolic. So what is the meaning of that total drag? The meaning of total drag is the thrust required. The thrust required for an aircraft is directly the total drag. Okay, so once we know the total drag, then we have to compute the required thrust. The available thrust must be greater than thrust required. So we have to find that point, and the point where total drag and available thrust and the total thrust, the required thrust coincide is called a cruise speed. So at some cruise speed, we may have an intersection between total drag and available thrust. Available thrust is from the engine, right? So that is called a cruise point. In order to know that, we have to know the drag profile also. So that is what we call drag polar. Thrust is the forward motion. We already discussed it. So thrust equation is equal to m dot VE. This m dot indicates the mass of fuel. We are not considering the total weight of, actually the total weight of aircraft you can take, no problem. But we consider the fuel which are consumed every moment. Okay, so fuel is continuously decreasing. As we consume the fuel, fuel is continuously decreasing. The initial fuel weight will be decreased from time to time. And when we arrive to the destination from one point to another, maybe we might consume all the fuel except the reserve fuel. Reserve fuel must be there in the aircraft. When we are landing at the destination, there must be some fuel. We cannot have empty weight aircraft.